but they're recreational. And that list could go on and on. But if we want to have some other amenities to things to help make things a little better, we're going to need some of these things in the middle. They're more engineering types. If we want to have air conditioning for cooling, if we want to have heating conditions, we want to be able to clean things a certain way. And the good old flush toilet. And lastly, irrigation of food. So we will make decisions. You will make decisions at your city level, county level, personal level, of what we're going to do with that. All right, some groundwater terms. On the right is a little cartoon from your textbook of the upper surface of the earth, a little soil horizon, and so on. I want to use this now to kind of as a beginning point for some other groundwater terms. We refer to the upper part of the earth as a zone of aeration. And it almost sounds like air, doesn't it? Well, think about it that way. Aeration, air, gas. It's the upper part of the earth where you have this soil and rock that's mostly filled with air. Yes, water will percolate through it. There'll be a little water in the upper part by surface tension sometimes. That's the zone of aeration. Now, below the zone of aeration, further down, is the zone of saturation. That's where all the pore spaces, theoretically, are completely filled with water of some sort, some kind of fluid. And then the boundary between the two, the zone, the area between the two, is called the water table. That's what's in between. So in the diagram, on the bottom is the saturated zone. And sometimes we have some other names for these zones, depending upon what area of study you take, whether it's a soil class or an ag class. I'll mention a few of those in the next few slides here. But everything in red is the most important part. Now that water table is going to go up and down. It fluctuates. You get more recharge of the ground, it'll go up. If you don't have any infiltration of water for months and months and months, the water table goes down. And we'll see what that does. All right, porosity I already mentioned, but we'll come back to it here. It's the percent of total pore space. It's in the underground material. Now it could be unconsolidated sediment, or it could be solid rocks. It can be igneous, metamorphic, sedimentary, or any kind of alluvium. But it's that pore space. So really what another way of looking at porosity would be is it's a way of storing fluid. It's the capacity to store that fluid. Now look at pumice. Pumice is really full of holes, isn't it? Very porous. Great potential for storage. But if all the bubble walls are still solid, can water move through it? No. So we have to take into account what? That permeability term. It's kind of a measure of how fast fluids move through the pore space. In other words, are the pores connected? This is a capacity to transmit fluid. So porosity and permeability come into play as significant parameters for hydrogeologists when we study those rock layers and study those sediments that contain the fluids. So here's a type of material, a loose unconsolidated stuff called gravel. Got big grains, small grains. On the average, we say that gravels have a medium to high porosity. You could get fluids into them. They could store stuff. And they're pretty permeable. A lot of good connected pore space. So when we drill water wells out here, we would like to be able to drill down and find those gravel zones and then perforate and put our filter in at that spot and start drawing the water off from that point. So gravels are good. Sand, pretty good. Sands are medium porosity, medium permeability, but still good zones underground to get stuff out. Lastly, though, clay-rich zones. Clays are common to shales. Clays is just muddy materials. Initially, clay is like a sponge. But, you know, when you have a dry clay and you add water to it, it'll suck up and actually expands, physically expands. Once it expands, though, it shuts off any open space and it just shuts down permeability. So shales are not good zones we get fluids out of too often. They kind of tend to prevent the flow of fluids. So the best, of course, are gravel. Sand's pretty good, clay not good. Siltstone certainly not, as good. And some cartoons from your textbook. You've seen some of these before, maybe of, pore spaces in terms of sorting. This is what we look at. We want to analyze a rock and say how easily will fluids move through these little pore spaces. All right, some more terms now. I already used one early on. Aquifer. An aquifer is a material that has a high porosity and a high permeability. High porosity, high permeability. Rock layer out here called the Ogallala. The Ogallala in western Kansas, a good aquifer. Parts of the Dakota sandstone, good aquifers. Now we're going to start shutting it down a little bit. We're not going to stop it. We're going to retard it a little bit. So from the word retard, to stop, to slow, or to slow down a little bit, to cut it back, we have the word aquitard. So as the porosity and permeability begin to drop, we run into units that are aquitards. And of course, obviously, the last would be where we completely attempt to stop it. We exclude it. This particular material excludes the movement of fluid through it. So low porosity, low permeability. Now these are some averages. And so as a hydrogeologist, you've got to look at all those possible situations down there and classify that rock in your area. And you better know your geology. Because if we start computer modeling this stuff to figure out how water flows, we don't get this right up front, the real stuff, the real rocks, then the computer models don't mean a thing. And that's a difficult task. A lot of math, a lot of computer programming skills. And of course the geology behind that and the physics behind that. As we try to figure out how fluid's going to move through the ground so we can get it out. All right, so snow's on the ground, rain's on the ground. What's going to control how easily that stuff can infiltrate or percolate into the ground? This is a list of infiltration rates controls. Well, rate and type of precipitation. If it doesn't snow or rain for 10 years, you don't have to worry about any infiltration. You're not going to have any water. Now, obviously, if it snows or sleets, that has to melt versus just being water. If you get a deluge of 4 inches of rain an hour, a lot of that's going to run off very quickly. What's the best to have is a nice, slow, medium rain for days and days and days. So it doesn't flood. It's all soaking right back in the ground. That's the best to have. Again, porosity and permeability. The higher they are, the quicker stuff soaks back in the ground. Steeper ground is not going to sit there and pool and soak in, so flatter ground is better. It'll stay there longer, have a higher chance of soaking into the groundwater system. If things are hot and we have lots of evaporation, all right, that's going to go back into the atmosphere. That's not good. The hotter it is, the drier the air is, the more and the greater the plants in one area. I know along the Colorado River they talk about phreatophytes, these particular plants. They're tamarisk plants that were brought in from a foreign country to kind of bring vegetation along. And it's like a weed, it just grows everywhere, but it just sucks up water like willows like you can't believe. Cottonwoods are good users of water. So you think about how much vegetation you want. The greater the evapotranspiration rates, the lower the infiltration. And of course the presence of vegetation. And so that's kind of an oxymoron kind of thing about what I just said about the transpiration part. Vegetation can help keep things from running off to have it soak in the ground better, but if it's got a root system and it's using the groundwater and pulling it back out, well then it's kind of going against it. So it's not that easy to calculate all this stuff. There's a lot of variables to think about. All right, this cartoon I want to use to show you two things, so to speak. The top one, up there in the top one, the rock underground is limestone. Brittle, fractured limestone that we kind of know that you can have cavernous types of features form, sinkholes. They don't show any caverns or sinkholes in the pictures, but fractured, brittle limestone like that with lots of joints and interconnected pore space that you'd get from that, water's going to move really fast through that. So remember, water moves faster through limestone than what we see on the bottom, which is sandstone or sands. Water will move faster through fractured limestone than it will through sandstone. I do that because I know I've got a question like that on the exam. And they use these figures in your text. How fast is fast? How slow is slow? I've got some general rates you do not have to memorize. I'm not going to ask any questions about centimeters per day type questions. But 10 to 100 centimeters per day, it goes from a slow to very slow rate. And then we can have fast, medium fast, and so on. But, again, you don't have to worry about the numbers. But I show you this slide in case you ever buy some property and somebody's got a septic tank uphill from you, up gradient from you, up dip from you, whatever the structure is, which way the groundwater is going to flow, and you have a freshwater well, and you have limestone terrain below you, chances of their materials leaching out of their septic field, and that depends upon the age of their septic field and the septic tank quality, and it's a big issue in the country when you're away from cities systems with the sewer and water lines. You're going to get a polluted well a lot quicker if you had limestone as opposed to sandstone. So remember, when you're buying land, you need to think about things like this. They do crop up in your life. And it may not be just some old, garbage stuff. It could be something very toxic. I've had students in my past come to me after this class and tell me, yes, I lived in the country and I got this physical disorder because of a certain kind of old dump or a well that was getting into our water well. We didn't know it till we ran some special tests. And you can send off and have your money sent to various things in the state to get your water tested. You can go to the Kansas Department of Health and Environment office and they'll give you a kit or they'll give you an address to where to get a kit. So think about, if you're living in a city, city waters tend to be better. Yeah, there's great springs out in certain countries and water's fabulous. But once in a while, accidents happen. And you're the ones to think about it. So think about your water quality. All right, these two cartoons. Very similar, wet period, dry period. I want to talk about an unconfined aquifer right now. An unconfined aquifer means that water soaks straight into the ground, straight into that aquifer. There's no sandwiching of aquatards or aquacludes or anything like that. It can soak straight in. It's unconfined. I'll show you a picture of a confined aquifer in a little bit. So in this diagram we have unconfined aquifers both in the top and bottom pictures. In the top picture it's raining. There's lots of rain. The water table's high. Both those wells, whether it's shallow or a deep well, they're getting water out of there because they can penetrate below the water table into the zone of saturation. There's even a spring sticking out of the side of the hill where the water table comes in contact with the hill. And there's water in the stream. That water, a lot of that water isn't just from runoff. There's, it's not raining in that it's raining up in the mountains per se. But let's say all the water's going to the left. You can still have water in that channel if it's not raining. Why? Because it's soaking up through the bottom of the channel. That condition is referred to as an effluent stream condition. Now let's get a drought going in the bottom right-hand corner. No more infiltration. People are using the water. Things are drying up. The water table keeps going down and down and down. What happens to the one of the wells? It's dry. Happens all the time. You have choices. You wait. You go buy your water. Or you spend money to drill a deeper well, or you hope it rains. Look what happened to the stream. There's still water in it, but where's the water going now? It's coming from the stream, lowering the level of the water in the stream, but it's moving downward into the ground. Now there is one thing I don't like about this diagram, because the water is moving out of the stream, right in this influent condition. There should be a little bump or a mound in the water table. The water table should bulge upward a little bit below that, because this water's coming down and recharging that little local spot. And I'll try to do that with another diagram later on, give a name to it in fact. So wet periods, dry periods change the conditions of this. In the lower left-hand picture, I've got what happens when you get a special little condition of having an aquifer kind of elevated above and trapped with an aquiclude below it. It's a little separate thing, not part of the main groundwater system, just a little localized one along the hillside here. And you can see about right here, you've got a little perched, elevated, aquifer. That means it's porous. Water percolates down here. Some seeps off into the main system, but other seeps out and comes out on the side of the hill as a spring, because this zone below it is an aquitard or an aquiclude. So it can't soak through that. So sometimes if you're seeing little springs along the sides of hills, it could be a result of that one you see up on top, or a little perched kind of water table. If you're ever traveling to Denver along I-70, before you get there, close to Glenwood Springs, east of it, there's a hiking trail that goes up to a place called Hanging Lake. It's about a 2-mile hike to a neat spot. It's a pretty tough climb if you've ever been up there, but it's kind of fun. And coming out of the side of the hill, you can see 2 pictures in the bottom left. Water's coming straight out of this huge cliff. This cliff of rock goes up hundreds and hundreds of feet above it. In fact, another 800-900 feet before it gets to the top of the mesa, the mountainside. And so water's coming through the ground, it's leaking right out of the side of it. They call it spouting rock locally. But it's created this beautiful kind of turquoise-looking little lake up there, this kind of spring-fed lake. In the bottom left, you can see a bunch of cutthroat trout, and if you're into fishing, but I don't think they allow you to fish in there, though. Kind of a little protected area. All right. Opened with an artesian well. What's an artesian condition to make an artesian well? Well, an artesian condition is any condition where groundwater rises in a well above the level where it was initially encountered. And you go, what? Well, let's go write that down. Focus on the terms in red. It rises above a level where it was initially encountered. So you can still have an artesian condition and not have any water flow out of that well. That's a non-flowing artesian well. You can have that. I'll show you a picture of what it looks like. And I'll explain why that happens. Okay? Rises in a well, not necessarily out of the well, just in the well, in the casing, in the pipe, above the level where it was initially encountered. And I'll show you a picture of a flowing artesian well, and then in the cartoon a non-flowing artesian well. Images from your text again. In the top picture is a larger 3-dimensional block diagram. The 2 lower ones are insets from parts of that. Okay? I want to bring your attention to the kind of Oreo cookie looking thing in the top diagram. The Oreo cookie layers. The blue layer is the cream filling in the Oreo cookie. It shows the blue arrows running through it, okay? You've got an aquitard or an aquiclude, usually an aquitard, that above and below that sandwiches a porous zone in between called the aquifer. All right? That's a confined aquifer. That inner layer is confined between 2 impermeable layers, as opposed to our unconfined aquifer we looked at earlier. Unconfined aquifers are real close to the surface. All right, now way up in the mountains, what we're going to get is rain, snow, whatever, and we're going to have that zone that's exposed, and we can have water percolate into that porous zone. And the water goes further and further and further down, right? Further and further down in there. All right, and what happens is pressure builds up. A hydrostatic pressure builds up in that confined aquifer. Now if we look on the left-hand side, well, let me get back to it. Let's talk about that pressure system. Remember, the pressure will be greater further away from the source and deeper down than it would be towards the source. In this diagram, they show something that you can't see in the real world. It's not visible, but it's a surface, an imaginary surface, that if you were to drill a well into this confined zone, because of that pressure, water would spout to a certain level or rise to a certain level. The level to which that water will rise is called the the potentiometric surface, and they show it with a kind of an imaginary plane of blue across the top, and you see it as the blue line in the cross sections. So now let's take a look at the left-hand side of the picture. Notice that you've got your water table there in that confined aquifer. That's where you first encounter it. That's where you would first encounter it. So on that left-hand side, the well goes down, you drill in, water will rise out of there, but the pressure is not strong enough. How high does it rise? Right to that blue line. Is it coming out of the well? No. How do you get it out of the well? You put an electric or a gas pump on it and pump it out. All right, now we go way on the right-hand side. The pressure is really built up by now. That pore pressure is high. You drill into it, and what happens? The water spouts out to the level of the blue line. That's that potentiometric level, the surface that we would see. Now what happens if you start drawing more and more and more and more water out of that? You use that water. Will that flowing artesian well continue to flow? No. If the pressure gets too low because you've used too much of it too quickly before it can recharge itself, you have to spend money to pump it out. And this is what's happened in the Ogallala Aquifer, and it's become an extremely important issue. There was a big article a couple weeks ago in the Hayes Daily about this, and how down in southwest Kansas they're going to have to change their crops from crops that use a lot of water to crops that use less water. They're going to go to cotton as opposed to corn. Well, this is a change in society. This is something that affects us. We have to deal with that. And that's what I said. This is a really interesting issue of how and where we will go. Another point of view of looking at this kind of artesian condition, if there's a little fracture somewhere where it actually can leak through for some reason, you might get a little artesian spring and oozing out if there's enough pressure, as long as it's below that dotted line where you first encounter the water table. So kind of a similar diagram to the last one. So those are good flowing artesian wells. Sometimes you can get some places where the artesian pressure is so high it actually blows up right out of the bottom of a river, like we see here in Mississippi. All right, new term for your vocabulary, drawdown. When you put a well into the ground, you're going to like penetrate through that water table system. You start drawing water out. Right around that well, there's a little cone that develops. Okay? The shape of it looks like a trumpet or the end of a bugle or a trombone or something, where it pulls down. So the pulling down by pumping out is called drawdown. The more rapid you pump, the more you pump, the faster the drawdown, the bigger the width of the cone of depression. So the shape of the feature is called the cone of depression. The process that causes it is drawdown. So remember, drawdown and cone of depression go hand in hand. A little offshoot here about some more groundwater conditions. I know I covered all the details back in the chapter on igneous rocks, so don't forget that about groundwater in terms of geothermal power and springs and geysers and stuff, but I'm not going to cover that anymore in this chapter. So just remember that that's still attached to the groundwater concept, though. I know a lot of jobs for geologists, besides being hydrogeologists, they go work for companies, state and federal, to look at geothermal conditions. All right. Water quality. Next time you go take a drink at a fountain, or you buy yourself a glass of bottled water, or wherever, hope you remember this, to think about the water quality and what we've got, okay?